All right, hello everyone. My name is Chris Dustin, and this is going to be an introduction to starting your first observation of supernova. So this video is not going to be super polished. This process is different, is changing as we work out the kinks and what can be done with iTelescope and what can be done with our other equipment and stuff like that. So, this is going to be a very polished video. I'm just going to try to get through all the information. Everything is actually going to be in the document that I should have sent to you already. I'm making this for like a general student, so I'm not referring to any specific student, even though there is a first student who is getting this for the first time. I should have sent this document to you, which is our observation procedures. It's 5 pages. The end is stuff that actually don't need to worry about. So I'm just going to start from the beginning and show you what you need to pay attention to and what you don't. And then I'm going to walk you through actually making the first observations using a possible supernova, which I've got over here. So let me give you a little bit of background first. So basically what, it talks a little bit about the blue bump that we're looking for. Feel free to read that stuff. Source identification. So basically the idea is that supernova go off all the time, and now humans have a way of finding them by using things like the Zwicky Transit Facility, ZTF, and also there's one other pan-stars is another one. They really look for asteroids, but they catch supernova on accident, and they tell us all about it. So some of these are going to be good for us to observe with iTelescope in a variety of ways, and I'll go through some of that. But basically, there's a source selection criteria which you can find using Laser. They connect to the Zwicky Transit Facility. Also, what I've been using a lot is the TNS Transit Name Server. So that's basically an email list that gets blasted around to everybody. Something like once a day, and that gives a list of new supernova sources as well as classifications. And for the purposes of this demo, I'm going to actually go to that. So here's my email. There's the transit name server email that I get. You can see that there are new transients reported: 1, 2, 3, 4, 5, 6. That's actually a pretty small number, but these guys are not classified. You can see they've got RA and DEC, discovery date, and those are like basically today, discovery magnitude, and then who discovered them. But it doesn't tell us what they are. It does tell us the filter sometimes they use. There's a Sloan filter, there's the G filter. But they also have some sources from earlier that have been classified. And these ones, they have the source name, RA and DEC, and then the classification. So here's a supernova 2, supernova 2P, 1A, 1A. And so we have a actual classification. So these are the ones that we know are the sources that we actually care about. So I'm going to use one as a test case, 2022 AHF. So if I click on that, I get to the page that I'm showing you on the right-hand side of the screen. So this is the transient name server. There's the supernova AHF. Now, this one is actually not a great option for the following reasons. It was discovered on the 24th of January, so at least a week away, right? It's February 3rd right now, so yeah, over a week. Really, the first 10 days is when we expect to see the blue bump. So this one is too late. It might have even gone off the 20th or something. We don't know, but it was bright enough to see on the 24th. It is past. It's too late for us for this guy. But I want to use it as a demo because it is a 1A, and it sort of illustrates some of the stuff that we're going to be talking about. So anyway, here's the position of this thing. RA and DEC, that's in hours. That's degrees. This is in degrees, I think. The RA converted to degrees. And you can read all sorts of interesting stuff about this if you want. There's a spectra. There's like some magnitudes and some photometry stuff down here that we don't have to worry about too much. But the pictures is what I'm going to be using to determine if this is a reasonable source. So you can see it's got a nice little fuzzy galaxy there. The source is actually offset a little bit. It doesn't show up in this image. Sometimes we can get pre-images like this that actually show us the dot that is the supernova. In this case, we don't have one. You can see it's offset in that image too. So the idea is that right there on the edge of the galaxy is where the supernova is going to be. Now this one might be a little too close to the galaxy. We might not be able to differentiate it from the background, but again, this is just a test case, and it seems like this might be a reasonable place that maybe we could do it. So anyway, so this is the source that I want to check. So let me go back to the document to go through this. So basically there's a 4-step process to deciding that you're going to chase down a source. And so, as you can see, the part of this process as of January 2020 is to have me do the first 3 steps. So visibly brighter than non-detection, TNS wouldn't show up unless it was there. Clear association with the distant galaxy, you can see that right there. It definitely is associated with that galaxy. Of course, that kind of makes it a problem because the galaxy is in the way, but if random dots show up in the sky that are not associated with galaxies, they are often not actually supernova. So we want to be sure we're actually looking at supernova. It'd be great to be outside the nucleus of the galaxies. But what happened is I had a former student who determined that that was basically never going to happen. So we're going to have to deal with the galaxies no matter what. We just want the outside part, the supernova itself, to be as enough outside the galaxy as we possibly can. So at this stage, I would send this this page to you and say, we now have a possible source. Can we see this thing? So your job will be to start with step 4. Determine if it is visible, which means over 30 degrees during a reasonable period of the night with one of the eye telescope locations. There's not a great way to do this automatically. If there's a telescope, Telescopius, that's a program that runs through iTelescope, it does not accept coordinates. The only way we have of finding the thing is with the coordinates, so we have to use the coordinates. There's 2 basic ways of doing this. The first one I'll show you is probably the quickest. Let me open that and move it over here. Which seems to be having some trouble loading. There we go. So star alt. So this will give you a plot of the altitude of the source at any location, not in the world, but at a bunch of specific locations that we actually care about. So night of February 3rd, observatory. If we look over here, I have a table of the 3 observatories that we use. So we use New Mexico, Spain, and Australia. You can set this to this location to get the correct place. So for instance, if I go to Apache Point, that's not actually at our observatory in New Mexico, but it's close enough. You can enter lat long if you want, but we don't really need to. So here we have coordinates. So we want to put in our source coordinates. I'm just going to cut and paste. So just give it a Control-C and then a Control-V. And that should be everything we have to do here. And then just click Retrieve. Okay, so we can see, what are we looking at? The moon is the dash. So we can see a setting moon and we can see a rising source. And there's other sorts of information on here. Number below the curves indicate the angle to the moon. So 166 degrees, that is very far away from the moon. Doesn't really matter because the moon is actually below the horizon, right? Down here. Here's the local time starting on that night. There's also a UT time, the 1, 2, 3, 4, 5, 6, but we can just look at the local time and we can see that from twilight, which is that dotted line there, and that dotted line there. So this is sunrise, this is sunset, twilight is there to there. The source is very high in the sky. And remember that observable is over 30 degrees. So over 30 degrees, it maxes out at 3 o'clock in the morning, but it's everywhere. So it's a really great source for New Mexico. We should also check the other ones. So max is at, and actually I think New Mexico is going to be the best. So I'm actually going to fill in the spreadsheet. Yeah, here we go. So if I do part A and I find a good observatory, if a source seems optimally placed where these conditions are met, meaning above 30 degrees, which it is, enter into the columns of the spreadsheet. So I also sent you a spreadsheet. So I'm going to pop over here and pull out that spreadsheet so you can see what to do there. So the spreadsheet has just a bunch of, and the spreadsheet is compressed. Sorry, I'm just trying to show as much of it on the screen as I can. You probably want to look at the whole thing. So fill out these columns first. So fill out these columns out to this bold line first. So first, this is a link out to the source. So I'm just going to cut and paste, Control-C there to give it the link. Date of first alert. This is a test, so it's a little bit stupid to use today's date, but I'm going to write, no, I should write when the actual source was first discovered, which is the 24th. So 124. Proposed observatory on the right, New Mexico. And then I'm going to write today, when is the object above 30 degrees? It's above 30 degrees from 22:30 to sunrise. So I can indicate that by 22:30 to sunrise. And then usually I like to put in the transit time. That's the highest. The transit was at 3 o'clock. So that's to know that the best time to observe is at 3 o'clock. That's a reservation thing, right? If we have time at exactly 3 o'clock, I'm going to reserve time right at 3 o'clock. And then any kind of observer notes, test case, close to galaxy, but 10 days after discovery. So this is not going to be a good option for the future because it's too far, but we want to make a note of what we're doing and why we're selecting. Okay, so I filled that out. Now let me just show you what happens when I do the other observatory. So I think New Mexico is going to be the best, but let's put in Spain. That's Las Palmas is the one that's closest, and some of these are like hard to find. Where's Las Palmas? I don't see it. Maybe that is an error. Oh, La Palma, I'm sorry, right there. So it's Roque de Muchachos. La Palma is the place in Spain, sorry. Anyway, let's retrieve it. Okay, oh my God, Spain might be even better. Look how high it is. Okay, because you can see that, I don't remember what the altitude was, but the altitude was like 70 or 80. Spain is even higher. I should note that Spain is even better. Spain may be better. But let's also look at Siding Spring. Right there. Yeah, and so typically, because that's on the other side of the Earth, it almost never gets over 30 degrees. So Australia is not a good option here. Both Mexico and Spain are good options. Okay, so now that we've filled out the spreadsheet, we can move on to planning the observations. So we want to move as quickly as possible to catch it. So basically, when I give you the source possibilities, I kind of expect you to fill out this part of the table as soon as possible and do the next thing if you find a telescope that works as soon as possible. You know, waiting a day is not the end of the world, but you do kind of have to be on top of it. Here's the list of telescopes we can use. You know, I use 30, 31, and 11 and 21 quite a lot. Those are kind of my go-to. So that's probably what I'll be thinking about today. Once you've chosen a telescope, go to the Deep Sky Plan Selections section. So let's actually, because see, New Mexico has more telescopes, that's generally why I sort of think about New Mexico. So let's go to New Mexico. Sorry, when it's compressed like this, it's kind of hard to, sorry, I think that, yeah, the bar vanished because I couldn't, because I was in the abbreviated view, okay. So let's jump down. First, let's try 11. 11 is a little cheaper. So for the purposes of just testing, this might be the best option. Okay, I want to go to the Deep Sky Plan selection and make the plan. I guess it might be a good idea to check the reservations first if there's nothing tonight, since we have so many. Oh, see, there's apps. Oh, right in there. See, that is actually probably enough time. So I think it might be worthwhile for us to get in there. Now, I can't reserve time without putting a plan, I don't think. Yeah, you must select a plan to run. So I have to actually make a plan. So I'll go to the plan, which is click Deep Sky. Name the file source whatever you want. The recommendation is basically to use the name of the source as the file name, and also the target probably. And sometimes for the target, I actually delete the spaces just because this gets passed to a text file. So I often just do that everywhere. I worry a little bit about the spaces. So now we want to put in coordinates, right ascension and declination in degrees. But notice that the right ascension, there's some words here too. We need right ascension and declination in hours and degrees. And that is actually not what the coordinates are given here. This thing is in hours, but not decimal places. So what you want to do is you have to go over to a converter and convert this into hours and degrees in the right format. But this is pretty easy. You just click this. So I clicked the converter. Now I'm in the converter, control click on the, control C on the right ascension degrees, put them in, click search, and then you'll get it converted into a whole bunch of different ones. The one you want is the one that looks like hours, but is decimal places. That's this one right here. So you can see it's 1050, that's 1050 minutes out of 60, converted to 10.8 with all the other decimal points to put in. And this is degrees in, declination in degrees 25.1. So it's 25.19 is 11 minutes out of 60 minutes. Anyway, so you can click this button. That will copy it into your clipboard, and you can go back to iTelescope. Control V. That puts the whole thing in there, and you can see it did not work. It is still in the other units. That's kind of frustrating. That's probably a Linux thing. I suspect if you just click it and do it right, it will, oh my God, it is not doing it. That's interesting. So in that case, I'm just going to highlight, Control C, click, yeah. So you see it put the whole thing in there. So I want the first number to be in the first box. So I'm just going to do that and delete the rest of it. and the second number should be in the second box. So delete any blank space at the end, and then delete all this down to there. Okay, so now we have the coordinates in hours and degrees. You can note on the sheet, like this little footnote, I screw this up all the time. I always forget to convert. So don't worry if you screw it up, but just, yeah. You can save this file and edit it directly by create the plan for later and then editing it on your computer, but that's a little tricky because you put some extra spaces and stuff in the file, and you might screw it up. So it's probably wisest to do the process I'm doing here. So for the filters, we want the bluest possible. That is probably going to be U, and the reddest possible, which is probably going to be like I. In this case, yeah, I is better than R probably. We're kind of evenly, so maybe just either way. Okay, so now we have to pick how many times to filter the duration. So that depends on the magnitude of the source. And here we have some guidance on magnitudes and exposures and what the signal to noise ratio is. This guy's magnitude last studied was 18.2. That's pretty dim. You can see we have an 18 here where we did 1 times 300, so 1 exposure at 300, but this signal to R is terrible. You can also see the binning is 1. So higher binning means lower resolution, but higher sensitivity. We basically always want to do higher binning. So this is probably why this one is so bad. The signal to noise ratio is so bad. We want this thing to be like 50 to 100. So like these numbers are good. This number is bad. So basically at 18, we are super dim. So I don't have an example of a good observation at magnitude 18. Maybe this would be a good test for that. But you can see when you get down to magnitude 13, 3 times 180 is an exceptionally good signal to noise ratio. So I think what I'll try here, and this might be a little bit of an experiment, but let's try 2 times 300 and then increase the binning. So all three of those things should increase the sensitivity and increase the signal to noise ratio. Higher binning, more filters, and longer duration. Well, the same duration, I guess, but the total duration will be longer. 2, 300, and then 2. I usually stop at 300. I don't go higher than that just because, 5 minutes is a long time. You screw up one of those and you lose a lot of time. So that's sort of why I do that. And we can use this as a test for this case, just we can add another line to this table once we're done. Yeah. Okay, now, so some of the things that might not be in here yet is we also kind of want to do plate solve, and we also kind of want to do dither. So that is just to avoid the problem of dead pixels. So dithering moves the telescope a small amount in between each observation so that if there's a dead pixel right on your source, okay, you'll lose one observation, but you won't lose any others. So we generally want to click those. Okay, create the plan for later. Plan is saved, and now we go over the reservation time and reserve time. Now we want data for as many as the next 20-ish days as possible, and the observer can decide how to manage that. So basically, it's your job to manage the idea of having 20 days of observations. The way I would do it, and you can copy me exactly if you want, reserve around 5 days immediately with either 30 to 60-minute reservations using this plan. So gonna pop over to iTelescope, and sorry, I'm there already, and actually do that. So I do it for 5 days, and you can see that I'm not really going to get 5 days. Oh, unfortunately, my M87 observation is right there already, so I can't do more time in there. But anyway, so I'm going to put it right here. And it was AHF. And selecting reschedule to get it to bump to the next open day. That's a little bit strange because I'm going to be doing 5 days in a row, but that's okay. I'm not gonna actually do 5 days. I'll do as much of 5 as I can. Yeah, this is gonna be a little stupid. I will get some time in there to run the observation, so I'll do it, although it will probably not be enough to fill it, and that's okay. And then I think I'll just stick with 3. Normally I really would do 5, but because I have an observation time here, and this is just a demo, I think I probably will not fully do the other 5. So 3 is probably enough. Okay, so now this first video is over because we have reserved the time. We've got as many days as we want at the beginning. The next thing to do is to check after the first night. Now, of course, I'm actually doing this right now, so the next video is going to come tomorrow or whenever the observation actually happens. But this is the first part. This is setting up all the stuff you have to do for the first night. I guess also, yeah, that's it, right? So this is all the table in here is set up. Sorry, I'm sorry, I forgot something. When the first observation is set, enter these columns. I should put that in here. Oh, it says it right there. Sorry. Enter this information in the spreadsheet. Okay, so D11. And what I'm doing is 2 times 300 bin 2 U and I. You can see it for T17 actually did 4 times 300. Maybe I'm gonna have to switch that, but that's something else that we can, that's part of the test here. Okay, anyway, so I'm sorry that I'm sort of being a little scatterbrained, but I think that's everything I wanted to say. Basically, you follow the instructions in the document, but I also want you to have a video so you could see me do all the sort of weird things like getting the conversion, getting the observability and then doing the conversion from write ascension to declination. But this should be it. I'll do the observation, and when it comes back, I'll have another video ready for you to analyze after the first night. Okay, great. Thanks very much. Hope this has been helpful, and thanks for watching.